it's wonderful to be here. Great to see Raghu, and great to see so many other people. I know that's still suffering from jet lag. I returned from India last Tuesday, and so please excuse if I say something silly. Okay, and some of you have heard this talk before, so I was trying for a new talk, but I haven't been able to finish it yet, so we'll finish on time. So anyway, so this is about the Edwards-Anderson model, and I'll tell you everything what it is. I'll not assume that you know, although in this audience people know a lot of things, but I'll just assume that there is at least one person who doesn't know anything. So, okay, so what is a spin glass? Spin glasses are magnetic materials with strange glassy properties, and I'm told that they actually exist. I haven't seen or touched one. So some common materials are these alloys, and one of the characteristic properties is the possession of many states with near minimal energies. Okay. So mathematical models of spin glass have proved to be very difficult to analyze, and because the materials are complex, and we have some great experts here, Gerard in particular. And they fall broadly into two categories, the mean field model, such as the SK Sherrington-Kirkpatrick model. And there is now a Nobel Prize and a Nobel Prize all associated with this model. And the more what are called realistic models, I don't know if they're really realistic, such as the Edwards-Anderson model. Okay. So tremendous progress has been made in the analysis of mean field models. Just two examples, Talleyrand's proof of the Parisi formula, Panchenko's proof of ultrametricity. The Edwards-Anderson model, on the other hand, has remained largely intractable. Okay, and I've heard it said that Chuck Newman, I think, discourages students, saying that it's a career killer, if you want to work on the Edwards-Anderson model. Okay, so well, so it's so problematic that even the physicists are not unanimous about the true nature of lattice spin glasses. So usually the way it goes is that physicists give us the conjectures, and then we try to, well, they don't give us, and they just put it out, and we take it, and then we try to prove things. But here they haven't given out; they've given out different things. One group has given out something, the other group has given out some other thing. So we don't know what to do about this. And you will see this coming up in this talk, this kind of problem where you don't know what's the truth. So it's like the Buddha, you go out searching for the truth. So in particular, there is not even a consensus that this model at all has features of a spin glass in some temperature dimension. So the spin glass phase is not proved. Okay. So what's the model? It's very simple to yeah.
When you say features of a spin glass, you mean features of the specific.
There are other things. So anything that's different, than a ferromagnet. Let's say a ferromagnet behaves in a certain way. Is there something different going on? So I'll take it very generously. Like you can be very specific what it means to be a spin glass, and Parisi has this whole setup. But as a mathematician, to even prove that it has something which is a little different, and I'll come to one feature. The physicists have a very strong demand on that feature, but I will put something very mild and try to prove it. So let's define the model. So one nice thing, there is only one nice thing about this model, which is that it's very simple to define. Everything else is problematic. So you take this box, 0, 1, L to the D, and let E be the set of nearest neighbor edges. For each nearest neighbor edge, you have a random variable attached to it, so it's a collection of ID random variables, and in this talk, we'll just take them to the standard Gaussian random variables. And the Edwards-Anderson Hamiltonian is just the Ising Hamiltonian, the Ising model, but with, instead of writing sigma I, sigma j, you stick in this jij in front. So it's like a model where neighboring particles have both ferromagnetic and anti-ferromagnetic interactions, and it's random. So one can talk about Gibbs measures associated with this, but I'll not even go into Gibbs measures. I'll just look at the ground state. So ground state of the model is state sigma, which minimizes this Hamiltonian, given the Jijs. So remember, we are just in a finite box. And since we're on a finite box, there are exactly two ground states, sigma and minus sigma, because we are putting free boundary conditions. So if sigma is a ground state, minus sigma is 1, and with probability 1, there is a unique one, because these are continuous random variables. And this is called the unique ground state pair for this finite box. And we can also consider some given boundary condition, or periodic, or whatever. But I'll just take free boundary conditions for now. Okay. So one basic goal is to try to understand this ground state, the behavior of this ground state. Is this clear? The question, like, it's an optimization problem where you try to minimize this Hamiltonian. It's a difficult optimization problem because the sigmas are plus or minus 1. Okay. Okay, so what are some available results about the ground state? So there are various results known about the Edwards-Anderson model. I'll tell you what the available results are prior to the work that I'm going to talk about. Eisenman and Ware proved that the fluctuations of the ground state energy are of order L to the d over 2. They proved both upper and lower bounds, matching upper and lower bounds up to constants, which show that the fluctuations, so there are L to the d spins, and you see that energy is a sum of L to the d things. And so if there is cancellation, you might expect L to the d over 2, but it's not really a sum, it's an optimization problem. But you can still prove that the fluctuations are of order L to the d over 2. Now, a standard approach in math physics is to consider the infinite volume, L equals infinity ground state. So you send L to infinity. Now, the notion of minimizing the energy no longer makes sense in infinite volume, but the difference between the energies of two states that differ only at a finite number of sites is well defined and finite. So although the energy of a single given state you cannot define because it's an infinite sum, but if you have two states which differ only at finitely many sites, then you can formally define the difference, and the difference comes out to be some finite number, and that you can talk about. So an infinite volume state is called a ground state if overturning any finite number of spins results in an increase in the energy. So that's called an infinite volume ground state. And one can study the infinite. So now it's no longer at all obvious that there is a unique pair, and that's in fact one of the big open questions. It's believed that in dimension 2 there is a unique, with probability 1 there is a unique ground state pair. In higher dimensions, it's not clear. In high enough dimensions, people believe that there is more than one ground state pair, but what about in 3 dimensions? I mean, 2 dimensions, nobody knows how to prove the uniqueness. So there's a lot of questions. So Eisenman and Ware proved that. Now, okay, so even before you study the ground states, in probability, you learn measure theory in your graduate class, and you find it very interesting, but later on you see that nobody proves anything about measure theory. Everything is measurable. So, but here, even that is very problematic. You have this infinite number of variables, and you have a set of ground states. Obviously, you have a set of ground states. That's just by a compactness argument. You have a non-empty set of ground states. Can you pick one measurably? Okay. Can you have a measurable map which takes the whole environment to a ground state? So I found, it's not published anywhere, but I found there are, and Michael Eisenman obviously knows it, that there is a way to measurably pick. But there is probably not a way to measurably pick in a way that is translation equivariant, okay? And it's not clear, how to go from an environment to a ground state. And so what Eisenman and Ware proved that one can construct a measurable map that takes the environment to a probability measure on the set of ground states that is equivariant under translations, okay? So such a map, this map, which takes the environment to a probability measure on the set of ground states, is called a metastate. Okay.
Positive temperature, this should be, the Gibbs measure, the map between the environment, the infinite volume Gibbs measures should be measurable. That should be.
Well, not not really if you want it to be translation equivariant. You see, so what you want is if you shift the environment, the map will also shift, the same amount. That I don't think you can do. Okay. So, so unfortunately, you have to recall all your measured theory to even understand what is written here. For the last 30 years, the mathematical literature has focused mainly on the study of these metastates. The problem with studying these infinite volume states is that infinite volume states, and it's not possible for me to explain here, but infinite volume states are all about looking at very tiny regions if you look in a finite box. So infinite volume corresponds to a very tiny region on a finite box, okay? So if you really want to understand everything that goes on in the finite box without looking at very tiny regions, you cannot really work with these infinite volume states. And that's one of the main difficulties with this thing, that ergodic theory gives us all these tools to study infinite volume systems, which are translation invariant and so on. But if you really want to work on a finite box, they are not sufficient, you see. Okay, so just as a simple example, the central limit theorem. So if you have a symmetric function of infinite linearity random variables, it's a constant, okay? It must be a constant, but summation xi over root n is not a constant. It's, the central limit theorem is an example where you have to go beyond this ergodic theory because, okay, so one of the main goals has been to show that there is exactly one ground state pair in infinite volume with probability 1, and the best progress in this direction is in these two papers, where they prove that a certain metastate on the 2D half plane, so if you consider half plane, the model in a half plane instead of the full infinite volume, which is kind of looking at the finite box but a small region at intersecting the boundary. So in that case, it's supported in a unique ground state pair with probability 1. And this is more or less a state of the art in literature. And there are a bunch of other results, but I'm not going to talk about, I don't have time to talk about those. In other words, we understand very little rigorously about the Edwards-Anderson model. And in particular, there is no proof that this exhibits any kind of spin glass behavior, which is, I interpret very generously as being different than a ferromagnet or anti-ferromagnet. Okay, so what is the marker of spin glass behavior? Consider the Ising ferromagnet on this lattice, where the GIGs are all 1. And the ground state pair is either all +1 or all -1. These are the ground state pairs, right? And take a region A whose size is of order L to the D, so which is a macroscopic region. So A, actually, I forgot to mention, A and A complement are both of order L to the D. So it's like a little blob. So suppose you overturn all the spins in A in some ground state. So in one of these two ground states, you take the ground state spins and you overturn everything in this region. And this increases, how much is the increase in energy? Because if you overturn in a region, you're going to get something which has higher energy. The increase is exactly equal to the size of the edge boundary, the set of all edges from A to A complement. Okay, so that's the increase in energy. Now, what the physicists tell us that in spin glasses, it's possible to overturn a macroscopic region of spins with an energy cost that is negligible compared to the size of the boundary. So this is the multiple valley picture. So you will have near ground states which differ in energy much smaller than what you would typically expect, okay, in the Ising model. So in the Ising model, you cannot do this. In the Ising model, you overturn a region of spins. The increase in energy is just the size of the boundary. In spin glasses, it's believed that there are these regions where you can overturn all the spins, and the contribution is much smaller than the size of the boundary. So for example, how much smaller? There are competing claims made by numerical studies that in 3D, the energy cost can be as small as L to the 1/5 or even order 1. And the size of the boundary is of order L squared in 3D. Okay, so it's much smaller than the size of the boundary. But the main difficulty is that there's an NP-hard problem, and it's really so. I mean, not just theoretically. It's a very hard problem, and I've seen the simulations in 3D. In 2D, there are efficient ways. But in 3 and higher dimensions, I've seen simulations with relatively small L, like L in the 30s or 40s, and I think 32 may be the highest number I've seen, but I may be wrong. So it's really hard to distinguish between L to the 1/5 and order 1 with L equals 32, okay? So, okay. Okay. So the physics heuristic for the existence of these low energy extensions is cancellations. So what they say is, just these cancellations because you have these GIJs. However, this is not enough justifications. So a few years ago, I proved this, but didn't publish, and it's in the new paper, that if you take any given region, the probability that this ratio, the energy from overturning all spins in a region, in this given region, divided by the size of the boundary, the chance that it's less than some positive constant, C1, is exponentially small in the size of the boundary. So for a given region, it doesn't happen. For a given region, if you give me some region, let's say a blob, and you overturn all the spins in the ground state, then the energy contribution from the boundary is still going to be of the order of the size of the boundary. It's exponentially unlikely to be anything smaller than that, okay? So it doesn't happen. The cancellations don't work for a given region. Is this clear? The statement? Okay. So even though the couplings are both positive and negative, there is overabundance of positive contributions, so that for any given region, it's extremely unlikely that the energy difference that you get from the boundary is much smaller than the size of the boundary. So for a given region, overturning the spins in A incurs an energy cost of the order of the size of the boundary with probabilities extremely close to 1, just like in ferromagnets. So even if the multiple value picture holds, it holds only for exceptional regions of overturned spins, okay? It doesn't hold for any given region. If you give me a region with high probability, it doesn't happen. So given the theorem in the previous slide, it's not inconceivable that such exceptional regions don't actually exist because it is exponentially small probability, at least in certain dimensions or certain graphs. And that's what I was trying to prove for several years, actually. I was trying to prove that these regions don't exist. And that's the problem, when the physics don't tell you exactly what they expect. So I was trying to prove that, but with no avail. Maybe it doesn't work on all graphs, but maybe in sufficiently high dimensions, or who knows, in sufficiently low dimensions, or some other graph than the lattice, where you just have to. So you see the chance that it's smaller than this constant is exponentially small in size of the boundary. So if the constant, the exponent, is just big enough, then you can sum over all regions with a given boundary size, and then just by union bound, you can show that such regions don't exist. However, I proved last year that these regions always exist. So, I was stupidly trying to prove something else, the opposite. So what you do is you take this box, and you take this ratio for any region A, you take this ratio, the contribution from the boundary, contribution if you overturn all the spins in the boundary, divided by the size of the boundary, and you take the minimum possible value among all sets which are macroscopic in size, that is, whose size is between 1/4 and 3/4 of the total volume, okay? So for each region whose volume is between 1/4 and 3/4 of the whole volume of the box, you take this ratio, the cost of overturning all the spins in the ground state in that region divided by the size of the boundary, and take the minimum to find the worst offender, okay? And then you can show that this is actually pretty small. The chance that it's bigger than L to the minus half root log L is small, and this K you can make kind of large, okay? So, and then for periodic boundary, you can slightly improve it. But there are these exceptional regions, always, in any dimension.
So in those exceptional regions, the cancellations work.
The cancellations work. Yeah. In those.
Is this one not completely wrong?
No, they're right. But I'm sure there are other papers where. So, okay. So this, yes.
I don't understand. You showed that the physicist did numerics showing that actually the contribution is very small, and you showed a theorem that's saying that you need to choose a very specific set that the contribution is very small.
Yeah. So they. No, they are looking among regions. So they are also looking among regions, and they are finding these regions. So they know that these regions are rare. That's known. That's not unknown. So they know. So it's tough to find. That's why, So it's tough to find these regions, and the numerics, they find these regions, and Yeah. Yes. These are fractal regions, and I have some basic results, but I don't have a very good understanding of these regions. Okay. So how many components, whether there is one large connected component or breaking up into many small components, I don't know. Okay. So all I know is that these regions are not easy to find because given any set, it's very unlikely. So if you have to find them, you have to look in a very large class of sets. If you just take all rectangles or all triangles or all polygonal things, you will not find them. Okay. So these are very hard to find and therefore fractal. And that's what a fractal is. I think sets that are hard to find. Okay. So any questions about this? Okay, so this is if you can say this is spin glass behavior, okay, you may not say this is spin glass behavior, especially if you're a physicist and you have high standards, but we have fairly low standards because we aren't able to prove anything. So we'll take what we get. But there's a first proof of spin glass behavior of any kind in the Edwards-Anderson model. Well, the thing is, you need to get this much better. So this L to the minus half is not sufficient. So the kind of conjectures that physicists are saying, it's actually much smaller than this. So let's see. So what the physicists say is L to the 1/5 over L squared. So it's like, even if you believe the 1/5 instead of order 1, it should be L to the 1/5 minus 2 here, whatever that is. Okay. So so instead of L to the minus half. So you need something much smaller if those conjectures, if you want to prove those conjectures. Yes? There are results in 2 dimensions, and it's even worse. What they say is that you can find these boundaries which are little o of 1 in 2 dimensions. So like small o of 1, these exceptional regions. I think what they say is in 3D it's big O of 1, but in 2D you can probably find contributions which are little o of 1, which is even smaller. But I'm not sure because the papers I've seen are all talk about 3D, and the 2D case I only heard over lunch. So I didn't see the papers. So yeah, citation to lunch. From David Hughes. Okay. So so let me tell you about another conjecture which I proved in this paper, and then I'll go into the proof. This disorder chaos, another physics conjecture about the ground state of the Edwards-Anderson model. It's sensitive to small changes in disorder phenomenon, sometimes called disorder chaos. So let us consider 2 different kinds of perturbations, both determined by a parameter p in 0, 1. In the first kind of perturbation, we replace each coupling by a small perturbation of the coupling by adding an independent Gaussian, and where the coefficients are chosen so that the sum of squares is 1, so that you again get a standard Gaussian. It's not important because the ground state doesn't depend on what factor you're multiplying by. If you multiply the whole energy by some constant factor, the ground state remains unchanged. But anyway, just for convenience, I'm taking this coefficient so that the squares sum up to 1. And if p is small, it's just a little perturbation of each coupling, JE. In the second kind of perturbation, each JE is replaced by an independent copy with probability p. So a very small probability, you replace a coupling by an independent random variable. Okay? So this is more common in the physics literature. The physics papers considered this kind of coupling, but this is more common in probability. We work with this kind of little perturbations in noise sensitivity. So in both cases, the perturbation is small if p is small. Now, the site overlap, so this is the overlap parameter that Gerard was talking about, introduced by Parisi, that let sigma be the ground state in the original environment and sigma prime be the ground state in the perturbed environment. And the site overlap between these 2 configurations is just the normalized inner product. So you take summation sigma I prime, divide by the number of sites, and this is number between -1 and 1. And the site overlap is said to be chaotic with respect to small perturbations if this overlap becomes close to 0 with high probability for some p close to 0. So a small perturbation will make the new ground state almost orthogonal to the original one, okay? So does that happen? So this was conjectured by Fisher and Hughes in 1986 and Bray and Moore in 1987, and there are various numerical studies, so there isn't much controversy about this. This people believe that this is true, and I'll tell you the heuristic reason behind that. And this is the disorder chaos conjecture. So this is another thing that I proved in the paper, that if you take this ground state and basically if P is bigger than 1 over L, so P can be pretty small, but you just have to have P is much bigger than 1 over L, you have that the expected overlap squared is small. Okay, so it proves this, this disorder chaos in the Edwards-Anderson model. Any questions about this?
Sorry, I forgot. What is R of P?
R of P is the overlap between two configurations. One is the ground state in the original environment, and this is the sigma prime is the ground state in the perturbed environment. So a little perturbation with P. And to consider two ground state and consider the normalized linear product. And this normalized linear product is small with high probability whenever P is much bigger than 1 over L. So RP is big, close to 0 with high probability if P is bigger than 1 over L. Okay? And again, if the what the physicists tell us, I don't know if it's exactly spelled out, but it's it comes from conversations and also from other evidence that this should hold for much smaller P, not 1 over L. So something like 1 over L to the D, or a little bit bigger than 1 over L to the D. It's not clear, but L to the minus 1 is certainly not the right answer. Okay, it should hold for much smaller.
Do they also predict temperature chaos?
Yes, they do. And there's actually a nice heuristic for going from disorder chaos to temperature chaos that Daniel Fisher explained to me, but I couldn't quite make that rigorous. But yeah, they believe in temperature chaos. But here, we are just considering the ground state. So, okay. Any questions? Okay, so let me tell you about the proof. In the physics literature, usually the multiple value picture is taken as a given. They assume there are these multiple values near ground states, and then chaos is argued to be a consequence of this. But I will go in the opposite direction. I'll first prove this chaos and then deduce these multiple values as a consequence of chaos. Okay. So this chaos thing, for those of you who know, it will be based on a kind of noise sensitivity argument using an orthogonal expansion. But I proved disorder chaos in a Schenker-Kirkpatrick model many years ago, and couldn't figure out how to do it for the Edwards-Anderson model. But so we'll see. But there is something simple that, as it always happens, something simple that I was missing. So simple case, chaos in one dimension, and this is the reason why the physicists believe that there is chaos. So consider the Edwards-Anderson model just on this line, 0, 1 up to L, with boundary condition that sigma 0 is 1. So you impose a boundary condition. For simplicity, I'll tell you why it's simpler. So in this case, the ground state has an explicit formula. It's given by the spin at site I is a product of the sign of the first coupling times the sign of the second coupling times the sign of the third coupling, all the way up to the sign of GM I minus 1I. And this is an exact formula for the ground state. And why is this the ground state? Because if you take sigma I plus 1, then all the signs up to I cancel out. Sign squared is 1. And you just have sigma I plus 1 is just the sign of GI I plus 1. And so when you multiply GI I plus 1, you get absolute value of GI. And that's the best you can hope to get. Okay? So this is easy to see that this is an explicit formula for the ground state. Now, why is this chaotic? So suppose we replace each Gij by little perturbation. You add an independent Gaussian random variable, and J0 is a very small constant. So what happens is that if I is large, in particular if I is much bigger than 1 over J0, a lot of these signs are going to be flipped. Okay? Not all of them. A fraction J0 of them are going to be flipped because you need the Gij to be close to 0. Like within 1 over J0 of 0. So a lot of them are going to be flipped if I is bigger than 1 over J0. And then if a lot of them are going to be flipped, this number of signs that are flipped is odd or even with roughly equal probability. Okay. So with roughly equal probability, sigma is going to change sign or not change sign. Okay. And that's why it becomes unpredictable what sigma I will be if you have the small perturbation and I is bigger than 1 over j0. So this argument was made precise in this physics paper of Bray and Moore with explicit estimates, and then this led to the conjecture that you can expect this to happen in higher dimensions also. But the problem is that this has no simple generalization because there is no explicit formula for the ground state in dimension 2 and higher. In 1 dimension, you have this nice formula, but in 2 and higher dimensions, there is no formula. Okay. And so this is why this is another question. So this is the main reason why that there's no simple formula for the ground state. And the second reason is that none of the standard tools that you use for spin systems, like correlation inequalities or monotonicity, or none of these things apply. So that's a problem. So now what I will show is that this argument generalizes in principle. The one-dimensional argument has a higher dimensional generalization in principle. Take any I and j, okay? Consider sigma I, sigma j, where sigma is a ground state. I and j are far apart. Think of two sides. Now you're the finite box. Consider sigma I times sigma j, where sigma is a ground state, as a function of these couplings. So as I mentioned, there are two ground state sigma and minus sigma, and for both, this number is the same. So there is that's a unique number. So you give me the couplings, I will give you this number. If I have a good computer, okay, and I know how to write programs. But okay, so this is a function of these couplings. It's a plus minus 1 valid function. Unlike in 1 dimension, we do not expect this to be a function of solely the signs of the couplings. However, it can certainly be expanded as a multivariate Hermite polynomial series. I'll tell you what it is. As I said, I'll not assume that you know it. Since these multivariate Hermite polynomials form an orthonormal basis of L2 functions of independent Gaussian random variables. So there is a polynomial, even if though it's a plus minus 1 valid random variable, there's an infinite polynomial series expansion of this. It's a multivariate polynomial in the couplings. And what I will show is that all terms in this expansion that have degree greater than or equal, so all terms in this expansion will have degree greater than or equal to the distance between I and j. So if you write down the sigma I, sigma j as a function of the couplings as an infinite polynomials series, then all terms in the series that appear are high degree terms if I and j are far apart. Low degree terms don't appear. So just as in the one-dimensional case, we saw that if I is large, then sigma I is a function of a lot of signs. It is kind of like that. That there are only these high degree terms appearing, and that's why it's so unstable under perturbations. Okay, so how do you prove that? So first, let me tell you about a little bit about this Hermite polynomial expansion. Let H0, H1, etc. be the orthonormal basis of normalized Hermite polynomials for L2 of the standard Gaussian measure on R, where H0 is starting with identically 1, and H1 is x, H2 is x squared minus 1 over root 2, and so on. So this is basically you take 1x, x squared, x cubed, and so on, and then you do Gram-Schmidt orthogonalization to get this Hermite polynomial basis. Now, if you go to higher dimensions, there's an orthonormal basis of L2 of all the couplings. It's formed by, the basis elements are now products of unidimensional things, okay? So this, if you're not familiar, it may take a little bit of time to see or grasp the statement. But so you take a function of all the couplings. Any L2 function has an expansion as a linear combination of these multivariate polynomials, where the multivariate polynomials are the following. So the index, instead of being non-negative integers, are tuples of non-negative integers attached to the edges, okay? So for each edge, you have a non-negative integer, and this whole tuple that you get is an index for your multivariate Hermite polynomial. Given this index, what is the polynomial? You apply the individual, univariate polynomials to the univariate, to the JEs. So you take, HNE of JE product over all edges, and that is your multivariate Hermite polynomial. And these multivariate Hermite polynomials form a basis, orthonormal basis of these L2 of J. Okay, so if you're not familiar, please take a look and let me know if there are any questions. Okay. So just to summarize, these multivariate polynomials are mutually orthogonal. That is, the expectation of the product of any two of them is 0 if the indices are different and 1 if the indices are the same. And they form a basis. So any L2 function, any square integrable function of the disorder J, all these couplings, can be written as a sum over all these indices f hat of n, where f hat is the Fourier coefficient, defined like this, times this multivariate Hermite polynomial. And of course, the coefficient is given by the inner product, just like any Hilbert space, the inner product of the function and the basis element. Okay? So, so you have this expansion. Okay. Is this clear? So we are going to apply it to the function which is sigma I times sigma j. You fix 2I and j, 2 points I and j. Sigma I times sigma j is a function of all the couplings. We are going to do a polynomial expansion of that function. So this infinite series on the right should be interpreted as an L2 limit of partial sums where the order of summation is irrelevant. So it's an identity in L2. So for simplicity, let us consider only the case of free boundary. Take any distinct I and j, 2 points. Let sigma be the ground state. Consider sigma I times sigma j as a function phi j of the disordered j. And for any index n, which is a tuple of non-negative integers attached to edges, let En be the set of edges E such that Ne is strictly positive. Remember, Ne can be 0 or non-zero. Okay, 0 or strictly positive. So you keep only those edges for which it's strictly positive, so that you get a subgraph of your original box. You throw out some edges, keep some other edges. And the following lemma is the main ingredient. So with this notation, phi hat of n, the nth Fourier coefficient of this phi, Fourier in the sense of this Hermite polynomial basis, is 0 unless both I and j are in the same connected component of this subgraph of the original graph. Okay. So you have this function. So nothing is random here. See, nothing is random. You have this function phi, which is a function of the j's. It has its Fourier coefficients, which are just numbers. Okay. And then for each index n, you define a subgraph, which is a deterministic graph, depending on your n. And then I'm saying that the Fourier coefficient, nth Fourier coefficient is 0, unless both I and j are in the same connected component of this subgraph. Okay. Any questions about this before I go to the next slide? So I'll now show you the proof. It's a relatively simple proof. Okay. So suppose I and j are not in the same connected component. Then there's a contour gamma separating the components containing I and j such that no edge gamma is in En. So basically, you can take the connected component containing I and everything else, and there are no edges going from this connected component to its complement. Okay, so that's your gamma. So suppose we replace je by minus je for each e in this contour. Let j prime denote the resulting disorder. So remember, this graph is not random. It's just depending on n. It's a fixed graph depending on your n. And suppose we, instead of je, we replace je by minus je and let j prime denote the resulting disorder. Note that j and j prime have the same law because these are Gaussian random variables. Now, if you do this change, however, the ground state sigma I sigma j, this changes to minus sigma I sigma j. So if you take a contour and you flip the signs of all the variables along the contour, the new ground state is obtained by just flipping either everything inside or everything outside. In either case, sigma I sigma j becomes minus sigma I sigma j. So that is phi of j prime is minus phi of j. However, hn of j is equal to hn of j prime because, everywhere on gamma, NE is 0. So the Hermite polynomial, the multivariate Hermite polynomial doesn't change if you replace j by j prime. So Hn of j equals Hn of j prime. So what do you get? Phi hat of n is expectation of phi j Hn of j, which is equal to this because j and j prime have the same law. But this is the negative of this, and this is equal to this. So you get minus. And this is minus phi hat of n, which implies that phi hat of n is 0. Okay? So unless I and j are in the same connected component, phi hat of n is 0. Questions? You have a question? Okay. Okay. So what is the consequence? So let's recall what we proved. We fixed some I and j, considered sigma I, sigma j, where sigma as a ground state as a function of the disorder. We took its Hermite polynomial expansion and showed that for a given index n, phi hat of n, so let this denote the coefficient of Hn of j in the Hermite polynomial expansion. And En denotes a set of all edges so that Ne is positive. And we showed that phi hat of n is 0 unless both I and j are in the same connected component of this subgraph of the original graph. So in particular, this shows, okay. So yeah, I'm not a combinatorialist, so I can only do these simple things. It shows that the number of edges is at least the distance between I and j. Okay, so I know that much graph theory, that if you have a connected component containing both I and j, the number of edges has to be the distance between at least the distance between I and j. Okay. So thus the Hermite polynomial expansion of sigma I, sigma j consists of only terms that are products of at least dij univariate Hermite polynomials. So every term in the expansion that's present has a lot of, is a product of a lot of things, univariate things. Okay. Any questions so far? Okay, so now that should give you the hint that it should be possible to prove chaos. And, I'll save you the trouble of, thinking. So I'll tell you how, how we do this. So, so let Jp be obtained from J by applying a perturbation P of either kind. What happens is that if you take the expectation of Hn of Je of P, there is something wrong. Hn of Jp, I think, not Je of P. Sorry. So the expectation of the Hermite polynomial expansion, this is univariate. Sorry, this is univariate. If you take Hn of Je of P given Je, in both cases, this conditional expectation is the original Hn of Je times the factor, scalar factor in front. So for the perturbation of the first kind, you apply that this Hn of Je, this Hermite polynomials form an eigenfunction basis of the Ornstein-Uhlenbeck semigroup. Well, so I'll not go into what that means. I think 60%, 70% of. When do I stop? Oh, I'm already over. Oh, okay. Okay, so let me skip. Okay, so what you end up showing is that the conditional expectation of sigma I, sigma j after perturbation given the original can be bounded by, it's because the only terms appearing here, I have a large factor of 1 minus p in front, 1 minus p to the some large power. So you can use this to prove, and then prove chaos. So anyway, if you are not convinced, it's a simple exercise to prove chaos from that lemma. And so this gives you chaos, and then I don't have time to go into the multiple values, but basically these exceptional regions, how do you find these exceptional regions? You apply a little perturbation, you look at the region which has flipped, and that's your exceptional region for the original system. Okay, and that's how it. Okay, so I'll stop.